The next function we'd like to add to our repertoire to build the Laplace transform table is a ramp function. And the ramp function just looks like this. So it's a linear ramp that starts at time is equal to 0 and just increases linearly, in this case with just a unit slope. And so we're interested in applying the definition of a Laplace transform in order to figure out what the Laplace transform of this ramp function is. This is a little bit trickier, and you'll need to pull back something from your knowledge of calculus. So go ahead and give this a try. If you get stuck, go ahead and unpause, and I'll give you a hint, and then you can pause again and give it another shot before you look at the answer. So my hint here is that you'll likely need to use integration by parts. So look that back up and pause again and give it another try and see if you can get the solution. So as I mentioned, you're going to need to set this up and solve it using integration by parts. And the reason for that is because the integrand, now the function you want to take the Laplace transform of, and then the definition of the Laplace transform, produces an integrand that you don't have a basic integral for. And so the easiest way to solve this is to use integration by parts. And so again, this is the fact that the integral of u dv is equal to u times v evaluated at your limits of integration, and then subtract away the integral from a to b of v du. So in this case, you always want to choose the polynomial here to be the u term so that you get to take the derivative of it, and what happens there is that the du is then just dt. So now we've gotten rid of this polynomial term. The exponential term depends on what you want to accomplish, but in this case it's then the dv term, because you can go ahead and take the integral of that, and now you get this minus 1 over s that pops out in front of the exponential. So when you plug that into the integration by parts formula, you get this, and the only thing to remember is again that you're going to go ahead and evaluate this quantity at these limits. So oftentimes one, or even in this case both of those terms, go to 0. This term goes to 0 at infinity because of this term. It goes to 0 at 0 because of this term. And remember, the quantity that you're plugging in here is t is equal to 0 and t is equal to infinity. So then we're just left with this element, which is now able to be integrated directly, and we go ahead and get this term, which allows us to now understand that the Laplace transform of the ramp is 1 over s squared. In this activity, we move on to deriving one of the fundamental properties of the Laplace transform that makes it particularly useful for dealing with differential equations. And essentially, we are interested in understanding what the Laplace transform is of a time derivative of a time function. So in this case, x is a function of time, so it's a time domain function, and we're taking the derivative of it, and that's why we have this dot here. So we are interested in understanding is, what is the Laplace transform of x dot? And we're going to be interested in writing that somehow as a function of the Laplace transform of x itself. And so leading up to this, we've done a few activities where we have used integration by parts to accomplish them. I recommend that you think along those lines and keep in mind that this has a derivative here that would be nice to remove if we wanted to express it in terms of the Laplace transform of the original function x. So go ahead and give this a shot using integration by parts to prove this relationship. And go ahead and pause the video now. So the solution for this looks very similar to the things that we've seen, like the ramp function and the sinusoid. Here we're interested in applying the definition. So again, we're applying the definition of the Laplace transform. This is the function that we want to know the Laplace transform of. It is abstract because now we don't know what x of t is. It could be anything, and so that's why we're proving a generic property this way. So we go ahead and put it into the definition of the Laplace transform. And again, this is, so in this case, we're going to use the integration by parts in order to get rid of this derivative. And so if we define dv as x dot of t dt, when we take the integral of that, when we integrate that, we now get that v is equal to x of t. So we get rid of that derivative by doing this, by choosing x dot as part of the dv term. So then that means that the exponential is going to be the u term, so we're going to take the derivative of it, and that's going to make du equal to, get this minus s down, times that exponential again. So when we substitute that in, we get this term is the u times v term, and this is the v du term. And in this case, when we evaluate this first term at infinity, we get 0 because of the exponential. But when we evaluate it at 0, the exponential e to the minus s times 0 is just 1, and we're left with x evaluated at t is equal to 0. And that brings in this term of minus x of 0. So that is the initial condition of the little function x of t. And when we solve this, what we notice is that we have this extra s that appears because of this. We get this extra s here. But then we get this integral, and this integral looks awfully familiar, and it happens to be the Laplace transform of the function x, which is what we wanted to accomplish. We wanted to express this, the Laplace transform of this function, in terms of the Laplace transform of the non-derivative, the original function x. So that's what we've done here. And if we go ahead and call this capital X of s, because now it's a Laplace transform, it's a function of s, we can now write the Laplace transform of x dot of t is equal to s times the Laplace transform of x minus an initial condition. And so this is really the heart and the beauty of the Laplace transform as you apply them to differential equations, because it allows us to write the Laplace transform of a derivative in terms of the Laplace transform of the original function. And what that's going to do is it's going to change differential equations into algebraic equations, because it gets rid of this derivative by essentially adding factors of s. And so we will generalize this behavior in the next video when we talk about the rest of the properties of the Laplace transform. In the last activity, we saw one of the most important properties of the Laplace transform, especially when we talk about it in the context of working with differential equations, which is the fact that the Laplace transform of a derivative of a function can be expressed as the Laplace transform of that original function x multiplied by s, and then possibly the inclusion of an initial condition x of 0. So an important aspect here is that this is little x, the derivative of little x. This is little x, so that's the time domain function evaluated at time is equal to 0. And this is the Laplace transform of x of t multiplied by the factor s. And so if you were to extend that same derivation for a second order derivative, so x double dot, so two derivatives, what would happen in that derivation would be that we would apply the integration by parts twice, similar to what we did in the sinusoidal case. And so what would then come out of that is that you would get yet another factor of s that pre-multiplies the Laplace transform of x. Also, because we already had this minus x of 0 term, that also inherits one factor of s, and a new initial condition is introduced, and that's the initial condition of the derivative. So if you remember back to solving projectile problems, you need to know the initial position and the initial velocity in order to solve that, because it's essentially a second order differential equation type problem. So whatever the highest order of your ODE, your derivatives of your ODE, you need that many initial conditions in order to properly specify the initial condition. So in this case, second order, we need two separate initial conditions for the original function x. So this is the little function x. This is also the time domain little function x, its derivative, whereas this is the Laplace transform. So as you keep getting higher and higher order derivatives, if you have m derivatives, this is kind of just generically showing you what it looks like, you have m factors of s pre-multiplying x, the Laplace transform. And then you get these decreasing powers with increasing derivatives on the initial conditions. And so this is a m-1 order derivative. So very elegantly, again, the important use of this particular property is the fact that we can convert a differential equation into an algebraic equation in the Laplace domain. So this seems like a very theoretical result that we're going to go through, but this is something that we'll use time and time again. And what this is essentially telling us is that if we have a function little y that's in time, that's our time domain function, if we want to know what y does in steady state, so once time goes off to infinity, so that's once everything's settled out and y achieves its kind of steady state, stable value, what value is that? That can actually be inferred directly from the Laplace transform function capital Y. And we do that by taking the limit as s goes to 0 of this product, s times the Laplace transform of y. And the proof is not particularly revealing to understand what this is going to do for us. It's going to do quite a lot, but I think it's still useful to see how the proof comes about so that you can understand where these results come from. So if we were to take a look at this, actually this whole value here, we could express that as being essentially the limit of this value here, the limit of the Laplace transform of little y dot. So the Laplace transform of little y dot, just from our past experience, is s times the Laplace transform of y minus the initial condition on little y. Okay, so that is essentially the limit of this is essentially what's up here, but then we're also adding this minus y, little y of 0. So if we rewrite what this Laplace transform is, we just insert y dot into this expression. And then now we're going to take the limit as s goes to 0. So we take the limit as s goes to 0, and that's going to essentially make the exponent of this exponential go to 0, which means that that exponential just approaches 1, because e to the 0 is 1. So once we are able to apply this limit, that removes this exponential, it turns it into unity. And so now we're left with just this integral, which is a function of time. It should be noted that you can exchange the order of taking a limit and integration when the integrand behaves well and is continuous at that point as s goes to 0. And so that's an important piece. So we're making an assumption there, but this holds for most of our physical systems that we're going to study. So now that this is just an integral in time, and we know that the integral of a derivative is simply just the value of that function evaluated at its limits, we get this quantity. And so we can rewrite y at infinity as y of t as the limit of t goes to infinity. So that's the upper limit here. And then the last part, we subtract off y of 0, and that's this second endpoint. And so now, the way that we set this up was we had this extra factor of minus y of 0. And now, once we do some simplification, we get that minus y of 0 term as well. So what that means is we can just take this piece, these essentially cancel out, and we can take this piece and the limit of this piece, so that's what this is, we set these guys to equal to each other, and that gives us the result, this theorem that we presented here. There's a similar result, the initial value theorem, that provides information about the function, time domain function, close to 0, based on the Laplace transform. So in this case, we're evaluating the limit as s goes to infinity of the product s times the Laplace transform. And that gives us information right after t is equal to 0 of the original time domain function. And this just after 0 is kind of important because a number of times we'll be looking at forcing functions that use this delta function, which gives kind of this instantaneous boost. And it's indistinguishable between a delta function and an initial condition sometimes. And so in this case, that information is encoded in essentially the value of that function just after t is equal to 0. When we take the Laplace transform of functions, and especially when we do the Laplace transform of differential equations, we rely a lot on the linearity of the Laplace transform. And we've talked about linearity a couple of times, and so this is the first time we'll be a little bit more rigorous about what that means. And one of the ways to express that is the fact that if I make a transformation, so in this case, the transformation is the Laplace transform. If I try to take the Laplace transform of a linear combination, so that means I'm going to take one function and add it to another, and I could put some arbitrary scaling in front of each of these, that the result can be computed instead as these scalar coefficients brought out in front, and then is the sum of these scaled versions of these transformed functions individually. So this means in order to find the Laplace transform of this whole function, I can instead find the Laplace transform of f1 and f2, go ahead and take these linear weights into account, and then add them together. And so it means essentially that the transformation of the sum is the sum of their individual transformations, and that you can also add these scaling weights onto them. And many of our important operators in math are in fact linear, and the linearity of the Laplace transform comes directly from the linearity of the integral. And so in this case, you should already know that if we have this quantity subbed into our definition of our Laplace transform, we can go ahead and multiply through this exponential to both of these terms, and that allows us to separate them into two separate integrals. And then these scalar factors can also be pulled out in front of the integral. And so it's really this linearity property that's going to make solving differential equations very easy, because we can take a Laplace transform of a very complex long ODE, and we can do that term by term. And in a similar fashion, when we go to come back to the time domain using the inverse Laplace transform, we will also want to take the inverse Laplace transform term by term. And so this is the real enabling property that makes that possible. The last property of both the Laplace transform and the systems that we're going to be interested in analyzing is the idea that we're going to focus in this class on linear time invariant systems. And what that means is that linearity really means that we can add solutions together, and we're gonna remind you what that means in one of the upcoming activities. Time invariant really refers to the fact that the parameters that describe the system aren't changing, and so one of the ways to characterize those systems are constant coefficient ODEs. So what does that mean? That means that you've got something maybe that looks like a x double dot plus b x dot plus c x is equal to some forcing function. And so what this means is a, b, c are all constants, and they're all just multiplying single terms rather than the combination of x times x dot or x squared or x dot squared. So the time invariance really refers to these constants, and the linearity refers to the fact that these terms all enter linearly. All of the derivatives terms of the variable, in this case x, appear linearly. And so one of the consequences that's important in here is the fact that inputs, when you apply an input, that has a nice property. If you apply two inputs, you can solve the response of those two inputs separately and add their responses together. And then another important consequence is the fact that if I shift by some amount a, so that's denoted here, if I change my input from this to this, essentially shift it forward or delay it by a, that all it does is it shifts the response. There's not any substantive change because I applied the input a units of time later. So this allows us, these are nice properties of these systems, but again, these represent fairly consistent systems, and they're the ones that we often see in the real world and in physical systems. Now that we're armed with the memory of what partial fractions means and how to accomplish that, we can kind of think about generally how to solve a differential equation. So if we start with some very generic differential equation, so in this case we have variables y, which are functions of time, and we have various different derivatives of those with these constant coefficients a, and we also have derivatives perhaps of our input u, and terms, constant coefficients indicated by b. We can solve for the transfer function of this by applying the Laplace transform. And so I recommend that you go ahead and sit down and do this if this next step is not particularly clear. But this means that we are able to solve for capital Y of s in terms of essentially a rational function of polynomials in S. And so the numerator is going to be order m, because that's the number of derivatives that we have of the input. The order of the denominator is going to be n, and that's going to be the highest derivative of the differential equation. And so remember, each of these terms, so for example, the y double dot term here, this contributes an s squared times capital Y of s. And so that's going to give us the s squared term down here. And then on the right-hand side, we're going to have this input u, our forcing function for this differential equation. And remember, just like we saw in the spring mass damper example, these could also have separate terms that might include initial conditions. So the initial conditions can also be perceived as an input to the system because they cause motion, they cause the dynamics. What we're going to be interested in doing is then factoring both the numerator and denominator into terms, and eventually we're going to start giving these names to these terms here. But effectively, these are all known based on the system characteristics and dynamics because they're all just based on these a's and b's. Now the question is what is this u of s? So once we're able to plug in what this u of s is, we can then combine what's called the transfer function, which could be thought of as either of these. That's g of s. And we're going to multiply by the known input. So we're going to say that we know an input that's impinging on the system. Could be a sinusoid, could be a ramp, could be a step function. And that means that this is now, so say it's a step function, or say it's a ramp. If it's a ramp, then the transfer function would be 1 over s squared. We know that from our Laplace transform tables. Now we would multiply that by our known transfer function, and that would just give us an even bigger ratio of polynomials that essentially looks something like this, but now with these extra terms caused by this input. Because that is not in our lookup tables, typically these are going to be complicated fractions and polynomials of, fraction of polynomials. We're going to need to break this up, and that's where the partial fraction comes into play. So we have this partial fractions that allows us to break this really big ratio of polynomials into individual ratio of terms that we can then find in our lookup table for Laplace transform. And that's the key. We want these things to be in our lookup table for Laplace transform. And then we're going to use the linearity of the inverse Laplace transform in order to individually take the inverse Laplace transform of each one of these. And there's some nice interpretation of what these mean, and we're going to keep thinking about this as we move along, that these are the different modes that are represented in the response. So we've used the linearity of the Laplace transform to essentially attack each of these terms individually. So on both sides of this equation, in order to come down to this transfer function. Then we're going to insert in our known input and possibly known initial conditions to get a large transfer function that represents the contribution of the inputs and the initial conditions. Then we're going to separate it with partial fractions. That's going to give us bite-sized pieces that then we can find and use linearity of the inverse Laplace transform in order to look up in our tables. And that is going to then give us back a time domain function, y of t, that is our solution to the original differential equation up here. So this is a lot on one slide, but this kind of captures the entire idea of solving a differential equation with the Laplace transform. And so it's pretty much the same no matter what problem you come across. What each step is will be dependent on what the particular problem is, but overall this is your approach to do this. So again, we may be either given or we may have to derive a differential equation model. We're going to use linearity of the Laplace transform to transform both sides of the differential equation into the Laplace domain. Then we can solve for y, the output, in terms of the inputs, possibly in terms of the initial conditions as well. That's going to give us a transfer function. Once we plug in our known input, we need to take the Laplace transform of that input to get the capital U of s that then we plug in and multiply by the transfer function. So then we do take this product, and if we also have initial conditions, we could also include those. That's going to give us a really large y of s that then we simplify, we break down by partial fraction expansion. And then we use the linearity of the inverse Laplace transform to individually take the inverse Laplace transform of each of these terms, again using our tables, to produce our final solution. And so notice the solution could be the sum of a number of different solutions. Each one of these could be corresponding to either different inputs or different terms that come out of the partial fraction expansion. This activity allows you to practice solving a simple differential equation using the Laplace transform. So this integrates all of the different steps that we talked about before. In this case, you have both an input u, and in this case, the input is a step input. And you also have a non-zero initial condition that you should take into account. And so go through the multiple different steps to solve this problem, ultimately coming out with a response due to both the input u and the initial condition y of 0 is equal to 2. So go ahead and pause, attempt this, and then we'll take a look at my solution. All right, so the first step is to go ahead and take the Laplace transform of our differential equation. So in this case, we have a single derivative that becomes s times the Laplace transform, and then we subtract off the initial condition. In this case, it is important to keep this because we have a non-zero initial condition. Then we just take the Laplace transform of the next term because of linearity. We get k multiplied by the Laplace transform. So it's important. The Laplace transform of the derivative gives us a y term, capital Y term, with a factor of s. When you take the Laplace transform of y, you still get capital Y of s. That's actually just by definition. So a lot of times people will make the mistake of just thinking that that's 1 or 0 or something like that, but it's not. The definition is the Laplace transform of y is in fact capital Y. And then we take the Laplace transform of little u of t, and we get capital U of s. So the next step is to solve for capital Y of s in terms of our inputs. In this case, our inputs, we're going to combine these two terms and divide by s plus k. And now that means that we have two terms, one that's due to our input and one that is due to our initial condition. Now we're going to plug in our different inputs. And in this case, I'm going to solve this by essentially each term. So I'm going to assume 0 initial conditions, and then I'm going to assume no input. But you could solve this directly if you want as well. So if I assume I have 0 initial conditions, I'm going to forget about this term for a second. And now the Laplace transform of my step function is just 1 over s. So that means if my Laplace transform is just 1 over s, then my combined transfer function with the input is going to be 1 over s times s plus k. And so that's not in my table, so I need to use it partial fraction expansion in order to separate this into a term that is for s and a term that is s plus k, because each of those could be in my table. So solving for my coefficients, I'm going to essentially multiply by s to get rid of this guy, and then I'm going to evaluate where that term was 0, so I evaluate at s equal to 0. That gives me 1 over k. Then I'm going to multiply this by s plus k, and that's going to leave me with s. I'm going to evaluate that at s is equal to minus k, and that gives me minus 1 over k as my second constant. So these are my two constants, and plugging those into these constants here gives me this partial fraction expansion. Taking the inverse Laplace transform means that I can take the inverse Laplace transform of just 1 over s. So that's the function 1. That's the step function. I take, again, the inverse Laplace transform in the next term, this term 1 over s plus k, and I get this exponential. And so that is the response due to simply just the input of a step response. So in the next slide, we're going to talk about what is the initial condition response without an input. So in the case where we want to consider the input, that is essentially no input, but the input being the initial condition. So here we're going to keep this term, and we're going to temporarily forget about this term. And so that means that now my y of s will just be 2, our initial condition here, divided by s plus k. And here I don't have to do any partial fraction expansion. This is already in my lookup table, and so that gives me this exponential solution. And so that means that the complete solution is then going to be the solution that we found due to the input plus the solution that we found due to the homogeneous response or the initial condition response. So that's the beauty of a linear system, is that when we have two different sources of input, and that could be two different u inputs, or it could be two different initial conditions, or it could be some of each. Whatever the initial, whatever that input is, something forcing the dynamical system, the response is simply the sum of their individual responses. And so again, you could have combined both of these terms into one giant transfer function and then taken the inverse Laplace transform, and that would have gotten you the same solution. But here what I'm showing you is that you can solve those separately and then add them together, and that's linearity right there. So this is the solution, and we will see a number of examples of how to do that in the homework, and then also on real application systems in the next set of slides in the next class. In this activity, we're going to return to our constant companion, the simple spring mass damper, or you can say it in whatever order you want, mass spring damper. And our interest here is to apply all of the techniques that we have learned about the Laplace transform in order to convert this differential equation that we've already now learned how to model. We're going to convert that into the Laplace domain by applying the Laplace transform to that whole equation. And then ultimately, not in this activity, but ultimately then we'll be able to solve that differential equation. So we're going to take that first step, which is to take the Laplace transform of this and solve for the Laplace transform of y. So that's capital Y of s. Remember that you've got three different things that are causing motion. So you've got the two initial conditions, the initial position and the initial velocity, and then you also have a possibly forcing function u of t that's being applied. So go ahead and derive this, and then we'll use this as an explanation to lead into the more generic solution of differential equations using Laplace transform. So go ahead and pause the video and take a stab at writing down the Laplace transform version of this differential equation and then solving for y of s. So as I mentioned in the intro, this is really about taking what we've learned about the Laplace transform and bringing it to bear on solving ODEs, so differential equations. And so I'll try to be rather explicit about each step that we're taking. So we're going to apply the Laplace transform to both sides. That's simply just like doing any sort of operation. So taking the derivative of both sides, taking the integral of both sides. Here we're taking the Laplace transform of both sides of the equation. So now, going from this second line to the third line here, this is linearity. This is the idea that linearity allows us to separate each of these terms. So in this case, we have these three different terms that are in the sum on the left-hand side. And linearity of the Laplace transform allows us to get to this equation here, where we've pulled the scalar coefficients, the mass, the damping coefficient, and the spring constant out, and now we're just taking the Laplace transform of each of these different functions, y double dot, y dot, and y. So capital Y of s is exactly the definition as being the Laplace transform of little y of t. So that's almost by definition, because again, y of s and y of t are things that we don't know. So the best we can do is represent it as in its Laplace form in the Laplace domain. The value and the importance of being able to express this derivative, the Laplace transform of this derivative, is the fact that we change that derivative into something that's in terms of y of s again. And so this is where we start talking about changing from an ODE or differential equation into an algebraic equation. And this is where that happens, because now there's no more derivatives, it's just essentially adding terms of y of s together. So this gives us s times capital Y of s, and this actually is a typo. This should be a minus y0. And so that allows us to express the derivative term. The second derivative term, then we get this second factor of s, so we get s squared times capital Y of s, and then we subtract away s times the initial condition in position minus the initial condition in velocity. All right, and so that then, once you plug that in, and you're going to solve for capital Y of s, and bring all the other terms to the other side, that's what gives you this equation. So if you need to see those intermediate steps, just stop and solve that out for yourself. So we're going to put all of these y of s terms together, and then that's going to be essentially this denominator, ms squared plus bs plus k. That's why we're dividing it, and that's why it appears in the denominator on all three terms over here. And so the reason why I've kind of factored it this way is that this tells me the term that's related to the input. So we didn't exactly talk about this, but remember the Laplace transform of the input is simply just capital U of s. And so you would need to specify what that would be. Would that be a step function, a ramp, sinusoid, whatever? So this is the term due to this input u of t. That's that first term. And then we also have terms that are due to any initial conditions that we have. And so we can actually separate those out into three different terms. And so one of the things that should kind of ring a bell from differential equations a couple semesters ago is the fact that you can separate the complete solution into something that is called the particular solution and something that is the homogeneous solution. The homogeneous solution is something that's due entirely to initial conditions, and the particular solution is something that's due to no initial conditions, but only to some sort of forcing function or an input. And so in differential equations, you would often solve these same kinds of equations here, and you would know that you could separate that into a piece due to the homogeneous behavior and due to the particular behavior. And so we're seeing that also in the Laplace transform of this differential equation. So again, this just goes into a little bit more detail there. So here, when we talked about this from the mathematical perspective, the solutions that are the homogeneous solutions are the solutions of the differential equation when there is no forcing function. So it's simply just what the system does when there is zero forcing. The particular solution is what happens when you add a particular form here. And typically, if you remember, these have a particular form that comes simply from this equation. And the particular solution oftentimes has a form that's due to what exactly this is. So again, whether this is a step function or whether this is a sinusoid or so on, the solutions take on a different form. But in general, and again, this is due to the linearity of the original differential equation, this sum is then the total solution. So again, the total solution can be broken up into these two different pieces. And so in everything that we're going to do in this course, oftentimes we will talk about something called the transfer function. And the transfer function really just means that it is a Laplace domain mapping from one signal to another. If we don't use it in a particular context, so if I don't tell you anything more than that, I just say the transfer function, then what I really mean is I mean, what is this rational ratio of polynomials that sits in terms of and expresses how the input gets mapped into the output, how some forcing function gets mapped into something we observe. In general, the transfer function, again, can really be anything that's referred to this kind of Laplace transform mapping. So technically, this term, you could talk about it as being the transfer function from the initial condition y0 to the observable output y. So you can think about, again, transfer function can mean all these different things, but if I say it without any context, it really means this particular one that expresses the input-output relationship of that differential equation, that system. And so what we're going to do now is we're going to better understand how to use these transfer functions, these ones as well as the ones for the initial condition, in order to actually solve to ultimately get little y of t. So little y of t, that's the time domain solution of this time domain differential equation that we had here. All of the in-between steps that we do with the Laplace transform are merely kind of in-between steps to help us get there. And so we take the Laplace transform to deal with something that no longer has differential equations in it, just has algebra. And then what we do is we rearrange this, we solve for y of s, we substitute in what u of s is, and now the interesting thing is then to apply the inverse Laplace transform to go from that function y of s that represents the signal y of t in the Laplace domain and take it back to little y of t. So what we're going to talk about now is the fact that when we have to do this inverse Laplace transform, we would like to have it in terms of things that we can easily find in our lookup table that we've been building. And a lot of times, once you get quite a bit of mess going on here, that doesn't appear in your lookup table. And so we're going to use something you've seen before but possibly forgotten, partial fractions, in order to break those up and get it into a form that's easy to find in your Laplace transform tables. So that's what's up next.